Okay, here we are to show. Now, do you remember what kind of function is this? It's called the. Do you remember what kind of function when y is equal to x? It's the identity function. Okay, so what is the limit of x as x approaches x of 0? You recall that this will just be equal to x of 0. Okay, so how do we show that this is true? Okay, how do we prove this? How do we prove that this is true? Okay, so let's look at what our given fixed numbers are. First, we have that L is x of 0, and we set our x to be x of 0 right there. Okay, and then epsilon is greater than 0. And notice that if I take the absolute value of f of x minus x of 0, what I'll get is x minus x of 0. Okay? It's less than epsilon. Well, what do you think should be our choice of delta then? Okay? Naturally, since we want to find a delta, okay, remember we want to find a delta such that, okay, that means such that for all x and x not necessarily equal to x of 0, the absolute value of x minus x of 0 less than delta implies that x minus x of 0 is less than epsilon. Well, what do you think our delta have to be? Then naturally we take delta to be equal to epsilon, since it's the identity function. Okay, so taking delta equal to epsilon would guarantee that our f of x minus L is within epsilon distance away from the limit point. So we have therefore proven that if we take delta equal to epsilon, then if x minus x of 0 is less than delta, then this f of x minus L is less than epsilon for any given epsilon greater than 0. And notice what we have here. Okay, let me just use my arrow, that way I can use a laser pointer. Notice that this horizontal strip is identical to the vertical strip because our epsilon is going to be equal to delta. And notice that it doesn't matter if our epsilon is less, or rather if our delta is less than or equal to epsilon, it still works, because as long as you want to make sure that this vertical strip lies within the horizontal strip. Take delta to be equal to epsilon. We can also take delta to be less than epsilon. It also works. That will still guarantee that the y values will stay within this horizontal strip. We can also take delta to be less than epsilon. It will still guarantee that this will hold. As long as we don't go beyond epsilon, we're safe. Now, let's look at another function. What is this function? It's our constant function. Okay, so what we want to do is show that the limit of f of x, which is k, as x approaches, say, any number, let's say x of 0, is equal to, what is the limit of a constant? It's just equal to the constant. Okay, so L is k, f of x, k, of course, epsilon is positive. Find delta. Well, look at this. If we take the inequality f of x minus L, what are we going to get? Look, this is f of x is k, L is k, minus k for the L, that's equal to 0. Then 0 is always less than epsilon for any choice of delta. What do we say then? Take delta to be any real number. Of course, delta has to be greater than 0, so that if x minus x sub 0 is less than delta, then f of x minus L, and in this particular case, k minus k is 0, which is always less than epsilon. So we have shown that if this is true, okay, for all x's, particularly x not equal to x of 0, possibly, then this inequality is less than epsilon. And look at this, look at our graph. It doesn't matter what our choice of delta, because all the time, every time we create this vertical strip, we project it up like this one, the y values are constant, so we'll always stay inside the horizontal strip. Even if your delta is right here, large enough right here, the y value, since it's a constant function, will always stay within the yellow horizontal strip. From those examples that we were doing, notice that I always start with this inequality. Okay, I always work with this inequality, then I find an interval containing x, in particular containing x sub 0, for which this is true and possibly not at x equal to x sub 0. Then after that, we find a value of delta greater than 0 that places, in other words, this interval with a width of delta about x sub 0, centered at x sub 0, stays in this interval that we got from step 1. If we find that delta, then this inequality will hold for all x's in the delta interval, except possibly at x equal to x sub 0. Back to example 1. From section 2.2, we said this already, that the limit is 7. And however close, we said that if it is 1 unit away from 4, we are guaranteed that the y values stay within 2 units away from 7, from this light yellow horizontal strip. If our choice of delta was bigger, like what I said earlier, except I didn't use the word delta yet because we haven't defined I haven't used the definition yet. Okay, so if our choice of delta was bigger, then what will happen to those y values? It's no longer, there will be, of course these y values will still be contained in the yellow strip, but these y values won't be in there. Okay, and if our delta would to be smaller than 1 unit, so it's right there. Okay, it's right there. Suppose less than 1 unit, we're good. We're guaranteed that these y values stay within the yellow strip. Okay, so as long as we don't go beyond 1, we can have a delta less than 1, it will still work. Okay,